Today we're talking about lesson 1510, which is mutually exclusive and independent events. So 1510, mutually exclusive and independent events. Now, the book starts out by talking about Venn diagrams, and you've probably seen Venn diagrams. And so let's consider, look at like the book example, let's consider the set A, which will be equal to the numbers 1, 2, 3, and 4. That'll be set A. Set B will be equal to 3, 4, 5, and 6. So there's our two set of numbers. Now, with the set of numbers, we can draw a Venn diagram. And the Venn diagrams look something like this box, and then we will have A here, and we will have B here. Now, A represents, the circle here represents all the numbers in A. And then B represents all the numbers in B, and then here, that's the intersection of whatever there's crossover. So we can look at the numbers. 1 and 2 are individualistic to A. So 1 and 2 fall just in A. Just in B, 5 and 6 fall just in B. And then we can see that the numbers of 3 and 4 are both in A and B. Therefore, 3 would fall, and 4 would fall right there in the intersection of A and B. Now the intersection of A and B, this part right here, okay, that middle part, you would write that as A, and then it's an upside down U, B. That's referring to the intersection of A and B. So the intersection of A and B would actually be equal to the set of numbers 3, 4. So that would be the intersection, okay, upside down U-shaped symbol. All right, so the intersection. Now, not all examples have any intersection. Okay, and if two sets of numbers, get rid of this. Let's say set A was equal to 1, 2, and 3, and set B was equal to 5, 10, and 25. If we were to draw a Venn diagram for that one, call that A, call that B. You know, in A, you would have 1, 2, and 3, those three numbers. And then B would be 5, 10, and 25, those three numbers. There would be no values in the intersection. Therefore, it would be, the book describes it as A intersection B would be equal to no solution or disjoint. They call it a disjoint set. Okay, so that would be nothing. Now, if we were to look at this, okay, let's use the same numbers. What if I asked for the union of A and B? So we were talking about the intersection. Now I could talk about the union, A union B. What A union B is referring to, it refers to all of A and all of B. So if we had 1, 2, 3, same numbers, 5, 10, 25. What it's referring to for A union B is all of the numbers that we see of the combined set A and set B. So all of those numbers. Therefore, A union B, in this case, not the intersection, but A union B would be equal to all of our numbers, 1, 2, 3, 5, 10, 25. Squeeze it in there. So all of the numbers A union B would be that. So there's some Venn diagram stuff and some notation things for that. Now there's some...
We still on for tomorrow?
Yeah, we're still on for tomorrow, Reese. I'm in the middle of recording a lecture.
Oh.
Yeah.
I'm bringing him to lunch tomorrow.
Okay, cool.
Okay.
We'll meet you at lunch tomorrow. All right? Yes. Sorry, I'm in the middle of recording. So, okay, we'll see you tomorrow.
Okay.
Honey teas.
Yep.
So the probability of A union B, like this, when we start talking about probability, there's a definition in your book on page 755, but it's equal to the probability of A plus the probability of B minus the probability of A upside down U, which remember, A upside down U is referring to the intersection for that. Okay, so that's one, the probability of A union B happening. And then that, though, if A and B are mutually exclusive, we're going to talk about mutually exclusive. Okay, if two events have no elements in common, that is, their intersection is empty, the events are called mutually exclusive. So in this case, okay, if A and B are mutually exclusive, then their intersection has nothing in common. So if their intersection has nothing in common, this would be 0, and so probability of A union B would just be probability of A plus probability of B. If their intersection is disjointed or no solution. So they're mutually exclusive, okay, that word mutually exclusive, if two elements or two events have no elements in common. So these would be considered mutually exclusive events because their elements do not have anything, there's no crossover in the elements. Those are called mutually exclusive. So the other definition is mutually exclusive events would be if A and B are mutually exclusive, then it would be P of A plus P of B, like that. P of A plus P of B, because the intersection part is gone. Okay, now if you have another word that we're going to talk about is independent. Okay, so independent. The word independent, two events A and B are independent if and only if. Okay, they're independent if and only if A upside down U, which stands for the intersection, is equal to the probability of A times the probability of B. What's up, Rebecca? You just want more candy? All right, you can have one piece of candy. Okay, now, when we look at this, okay, independent events, okay, two events are independent. We'll look at an example. If the occurrence of one event has no effect on the probability of another event, the two events are said to be independent. So if, in general, if the occurrence, okay, of one event has no effect on the probability of another event, the two events are said to be independent. All right, now the last word I want to cover before we do a couple examples is the complement. Okay, and the complement is referring to, okay, the complement consists of the elements of S that are not members of A. So the complement would be written with a bar over the top. So the complement of A, if you think about a Venn diagram, let's say, if you just had A, well, if you had A and B, let's say, and we wanted to do the complement of A, there's B. The complement of A refers to everything not in A. So everything not in A would be all this, including B and anything on the outside of B, and so nothing in A. All right, that's what the complement means. So if we had two sets, A and B, complement of A would be everything not in A. So we have that, just that space. That's the complement. And that can sometimes be useful when we're solving problems. All right, so enough about notation, Venn diagrams. Let's do some examples. Go to page 759. Open up your book. Page 759. let's take a look at number 2. Okay, number 2. 759, number 2, it says a single marble is drawn from a bag containing 3 red, 5 white, and 2 blue. So here we have a bag of marbles. 3 red, R, 5 white, 1, 2, 3, 4, 5. Devin, what do you need?
Nothing.
Okay. And then 2 blue, blue, blue. Okay, now, a single marble is drawn from a bag containing 3 red, 5 white, and 2 blue marbles. Find the probability of each event. Now, A says a red or blue marble is drawn. So what's the probability that a red or a blue? Okay, so we look at the set, how many things are there? There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 marbles. So what's the probability, okay, of a red or a blue being drawn? So red or blue being drawn, it's going to be equal to, there's 10 items, 10 marbles, and you could choose either 3 reds or 2 blues, so 3 plus 2, it's actually going to be equal to 1/2 for that. Okay. What about B? Okay, B says a blue or white marble is drawn. So blue or white, okay, probability of blue or white is equal to 1, 2 blues, 5 whites, so 5 whites plus 2 blues over 10 is equal to 7 over 10. And then C would be, what's C? It says a red, white, or blue marble is drawn. So what's the probability that a red, white, or blue? Well, if you wanted red, white, or blue, okay, a little patriotic there, that's equal to, there's 10 options for that over 10. 100% chance you're going to draw one of those marbles out. All right, so that takes care of that one. What about, let's go to something a little bit different. That was number 2. What if we take a look at number 4? So Norbert, what's going on? I'm recording a lecture.
Okay, go for it.
Are you, what's going on?
Oh, just stop.
Just checking in to say, will you be in your room after school?
Yeah, for a while. I think they're having a tennis meeting.
Okay, stop. I'll try to connect with you here in a couple minutes. I'm almost done. Okay, so for A, okay, it says there are 3 red, 2 blue, and 3 yellow crayons in a box. Jeff randomly, that was convenient. Mr. Norberg, Jeff Norberg just came in. Now Jeff randomly selects one, returns it to the box, and then randomly selects another. Find the probability of each event. The first crayon selected is blue, and the second is yellow. Okay, now, this is the probability of the first is blue, the second is yellow. What's important here is that we make a note, the crayon is drawn out and then replaced. So look at the total number of crayons. There's 8 crayons. Okay, if there's 8 crayons, then the probability that the first is blue, we look at how many blue ones there are. There's 2 blue, okay, out of 8 times, okay, so 2 blue out of 8. But then you replace it, okay, and then the next one is that it's yellow. So 2 blue out of 8 times, how many yellows are there? 3 out of 8. And so that would be equal to, you multiply those, 6 out of 64, which you can reduce to be 3 out of 64 divided by 2 is 32. Part B says, which one's part B? It says both crayons selected are red, so probability of red and red. Now you're going to return it, right, to the box. So if you're looking for red, then there are 3 red, so you'll go 3 out of 8, you return it to the box, 3 out of 8, and so it's equal to 9 over 64. What's the word, Brad? raining.
Yeah, that's what I would have.
You still want to go in the pouring rain.
I don't know, do you want to or no?
I personally don't. I know Carson does. I'm a fair weather fan.
You know how to fix this brake?
Uh,
Fine, it's like shifted.
I'm gonna take a look at it in a second. I gotta finish this lecture though for you guys. Right?
Yeah.
This is for you guys. Number 12, page 760. Number 12, make this our last example. Since we've only been going for 15 minutes, maybe this won't be our last, but we'll make it one of the last. Okay, it says when Carlos shoots a basketball, the probability of a basket is 0.4. So he has a 40% chance that he makes it. When Brad shoots, wow, convenient again. Brad was just standing here, and now Brad shoots. It was Jeff Norberg, then Jeff, now it's Brad, then Brad. Too bad we don't have a Carlos in there. The probability of a basket is 45%. What is the probability that at least one basket is made if they each take one shot? Okay, so they're each going to take one shot. So what's the probability? Okay, now, when we do this, we want to refer back to our, where was it? The probability of any two events, okay, on page 755. Probability of A union B is equal to the probability of A plus the probability of B minus the probability of the intersection of A, B. So when we do this, this is what applies for us here because these are not mutually exclusive, okay? Because it's making a shot, so they're not mutually exclusive. So when we look at this, we can say, okay, what's the probability of Carlos? Let's think of this as Carlos and this is Brad. The probability of Carlos making a shot is 0.4%, so 0.4, plus the probability of Brad making a shot is 0.45, minus the probability of the intersection of B. Now, if we wanted to find the intersection of B, I'm going to write it down here, we'll have space. Remember, the probability of A intersection B is equal to the probability of A times the probability of B. So for that, we say minus 0.4 times 0.45. And that is going to equal then, when we calculate it out, 0.4 plus 0.45 minus 0.4 times 0.45. And it gives us a 0.67 or a 67% chance that one of the shots will go in. If they each take a shot. Okay, so if they each take a shot, that would be the percentage chance that they go in. Now, if you're confused or you're wondering, well, why don't I just add? You can usually do a little bit of guess and check and see why you wouldn't or that you wouldn't add. Because if they both took a shot, 40% and 45%, if you just added those, it'd be an 85% chance that it goes in. That's not very accurate because most likely, I mean, if you look, Carlos is probably going to miss, Brad's probably going to miss, it's under 50%. So if they both shoot, it's not like, oh, well, 85% sure they're going to make it. Or do change the numbers even and say, well, what if Carlos, just real quick, what if Carlos was at like a 60% shooter, so 0.6, and Brad was a 50% shooter, 0.5. If they both took a shot, what's the probability it goes in? You want to just add those two and say, oh yeah, perfect, that's 1.1, which is not approximately, it's equal to 110% chance that if they both shoot a basket, they both go in. I mean, I know Brad's good, but he's not that good to guarantee 110% chance that between him and Carlos, who must be pretty good too, that their shots go in. That's why you wouldn't simply add them. You have to subtract by the intersection for that. All right, let me get rid of this. Let's take a look at one final one. And which one do we want to look at? What about number 10? Then we'll be done. Number 10 says, from a 52 card deck, a card is drawn and then replaced. So remember, it's replaced. After the deck is shuffled, the second card is drawn. Find the probability of each event. So there's 52 cards. The first card is a 5. Okay, so what's the probability that the first card is a 5? Well, if there's 52 cards, so probability that first is a 5, and then the second is a 6. So the probability that first is a 5, remember you have 52 cards. I take one card out. How many 5s are there in the deck? You have to know that. There are 4 5s in the deck. Okay, now you replace it, right? And then when you replace it, you're going to draw, shuffle, and you're going to draw again. And you're going to see if the probability that the second one is a 6. Well, how many 6s are there? There are 4. Now you can reduce, it's 1/13 times 1/13, which would be 1 over 169 for the probability. So not a very good probability that you're going to get a 5, and then you're going to get a 6 after you replace and shuffle. I would not bet that much on that. Okay, B says both cards are clubs. All right, so probability that the first is a club and then second to club. Now remember, you are replacing the card. Well, how many suits are there in a deck? There are 4 suits, I'll tell you. So if there's 4 suits, that means there's 13 of each suit. So the first card you draw, what's the probability that it's going to be a club? Is a 13 out of 52. Okay, so 13 out of 52. Now, let me show you how. Some cards here. Oh. Stand by. There we go. Okay, I don't know how well shuffled these are, but here we are. Probability that it's a club. Okay, failed. Okay, the card goes back in, we shuffle it up. Oh wow, there was the club, that's what we wanted. Okay, we shuffle it back up. Now, there's still 52 cards in there. And what's the probability? This one's a club, there's 13 clubs. Failed again. 13 over 52, 1/4, 1/4, giving me a total of 1/16. That they're both going to be clubs. All right, that's it. Sorry for all the disruptions. Between people wanting candy, between Mr. Norberg just wanting to chat with me because I'm awesome, between Brad getting his mountain bike, I don't know. So, Jack failed again. Don't bet on clubs.